Hi everyone. Today we're gonna be talking about chapter 6. It's about optics and telescopes. So, mainly we're gonna discuss the two main telescopes astronomers use to do observations, and we're gonna also talk about the mechanism and how they work. We're gonna give some examples about some of the large telescopes we have today here on Earth. So, to start with this, let's first talk about the main purposes of telescopes. It's actually a simple idea. You can think of a telescope as a camera, and as you already know, cameras can be more sensitive than a human eye. So, as an example, if you look at the sky, a human eye can detect thousands of stars. But if you build a telescope and you use a telescope to observe the stars, you're going to be able to see millions and billions of them. You will actually be able to see galaxies, black holes, and so many other faint and further away objects that we have in the universe. So, so telescopes are very important because they can detect faint objects that a human eye can't see, and they can also detect objects that are really far away in the universe that also human eyes cannot see. So this is one important point for telescopes, why we use telescopes. Another important point for why we use telescopes, if you look at this graph, which we have covered in one of the previous chapters, we talked about the opacity of the atmosphere. We have agreed that the atmosphere is opaque to some wavelengths, and it is also transparent to other wavelengths. So if you look at this part of the image, we have two telescopes that are above the Earth atmosphere. And such telescopes, like infrared telescopes or ultraviolet ones, these can detect wavelengths, colors that human eye cannot see. So not only telescopes can detect faint and further away objects, but they can also collect light that is invisible to human eyes. Something like gamma rays, X-rays, infrared, ultraviolet, and so on. And I'm gonna be talking briefly about this part in the upcoming slides. Okay? So, if you want to see how a telescope would work, look at this star right there. Stars like our sun are always shining, they are giving light in all directions. What you see here as lines are nothing but the photons, the colors coming out from the star. The main purpose for a telescope is to collect as much photons, as much light as possible from from the star we are observing. And as you notice, when the star is shining, it's giving so many photons, so many light, and then these photons are going and spreading in different places in the universe. Although this star produced so many photons, look here on Earth, this is our telescope, look how many photons we have received from the star. We have only received few photons out of the billions of photons that have been escaping from the surface of the star every second. And a telescope here will do its best to collect as many photons as possible from that star. So this is what a telescope does. It only collects photons, it collects colors and light coming from stars, galaxies, planets, and everything you are interested in. And this is exactly the same when it comes to cameras. Like, think of your phone cameras. The larger the camera, the more photons your camera will be able to collect, the better the quality of the image will be. So let me give you another purpose for why we use telescopes, and this is what I have already mentioned in the first slide. So this is an image for a galaxy taken with a visible light telescope. So a telescope that can observe red, blue, green, orange color, etc., the rainbow colors. So this is the image of it. If you're an astronomer interested in this galaxy, you point your telescope, you take the image, you study the structure, the colors, and so on. But the thing is, if we take an image for the same telescope, but using an infrared telescope, this is what we get. So in this infrared image here, you can see that there are a lot of radiation here actually coming from gases around the galaxy, and there are also more radiations and gases from this region. So if you would have only taken an image through an optical telescope, rainbow color telescope, this would be your image like that. But this wouldn't be enough for astronomers to actually understand and study all of the properties of that galaxy. So you better take images for the galaxy using an optical telescope and also using an infrared telescope in this region. Again, just let me remind you, holy, these infrared radiations coming from clouds, the colors are invisible for a human eyes. This is why we cannot see them here. While if you use an infrared telescope, these structures will be seen. So yeah, this is more about the telescope. So now I'm gonna tell you about the two types of telescopes that we use. One is called refractor with an R, and the other type is called reflector with an L. So here is a sketch for a refractor telescope. Well, mostly refractor telescopes consist of two lenses. This is the first lens right there, what we call the objective lens, and then you have another lens, what we call the secondary lens right there. So what happens is is the following: you put an objective lens here. This is the tube of the telescope. You point your telescope to a star. Let's assume the star is located here. The star is shining, is giving photons. These photons will be collected by your lens, by the objective lens, and this lens will automatically it will point all of these photons into a single point right there. And then what we do is we get a magnifier. We place the magnifier in this region, and then this image of the distant star will be magnified and we will be able to see it. I'm gonna repeat this when we talk about reflectors, and hopefully by then it will become more clear. But the telescope is mostly empty. You just need to know that it's a tube like the one you see here. You have one lens. Sometimes you put two lenses, but let's just assume only we have one lens. So this is the one lens. When you have photons coming in this direction, this lens is usually designed in a way that it will deflect these photons into a single point somewhere here. And then what we do is we put a magnifier at this point, and it will magnify the image of the photons that are coming from stars or galaxies that we are looking at. So what you need to know is that refractors use lenses, and refractors were the first telescopes ever used by people. Now, let's think about the why does it matter to have larger telescopes? You can also relate this to your phones. Sometimes you buy a camera or a phone with a camera with 10 megapixels, and then you buy a better camera that has 15 megapixels, and so on. So what's happening really is that the size of your camera is increasing, and as the size of your camera increases, the quality of the image will get better and better, and this is why. So this is telescope number 1 right there. This is telescope number 2. Obviously telescope 2 is larger than telescope 1. If you point telescope 1 to this galaxy, this is how it will look. If you point telescope 2 to the same galaxy, it will even look better than how it looked with the first telescope. And this is because we are using a larger diameter telescope in the second example here. A larger diameter, like you see here, will be able to collect more photons. So, for example, this galaxy, we are able to collect 1, 2, 3, 4, 5 photons. So 5 colors and 5 lights will be combined to give you a good image. If you use a smaller telescope like this one, only 1, 2, 3 of these photons will be able to be collected with your smaller telescope. So you're gonna have a fainter image, and so you're gonna have a more distant image like you have here. So the main purpose of increasing the sizes of telescopes is to be able to collect more photons, more light, and thus for you to have better images for the objects you are looking at. So the larger the telescope, the better the image. This is a rule that you can rely on. And when I say the larger telescope, I mainly mean by that a larger lens, which is located right there. The larger the lens, the more photons will be able to collected, the better the image will be when you look at those images. And this is a clear example of the same object. One here looks better than the other because the telescope used here is more powerful than the telescope we have over there. So yeah, this is the main reason why we tend to like larger telescopes. This is an example of a telescope, a refractor telescope. You see it's a very large tube. At this part of the tube we have what we call the objective lens right there, and this is similar to the lens I have showed you earlier. So this telescope is pointed, let's say the star is located here. So the star is shining, giving photons. This telescope will collect, this lens will collect these photons, and it will direct them all the way, to this part of the telescope. This is the eyepiece. This is where we put the magnifier in order to see that star we are looking at. So the larger the lens, the more photons will be collected, the better the image will be in the eyepiece. This is just an image of an objective lens of one of the telescopes we have in the Yerkes Observatory. It's an old refractor telescope. So yeah, this is how it works. Now, we have problems with refractors, and I'm gonna state few of the problems we have them, and you will be responsible for them. The first problem with refractors is what we call the mechanical problem. You see, this is a long telescope. It's mainly empty, and you can go back to the sketch I have shown you in the previous slide. It's mainly empty, but it has a very heavy lens at this part of the telescope. Since we have something very heavy at this end, and most of the telescope is empty, we're gonna have a mechanical problem. So the heavy lens here will be putting so much pressure on the tube that the tube might get broken. This is what we call the mechanical problem, because lenses are heavy, and if you put something heavy at the end of an empty tube, this heavy object will probably break your tube. So this is a real problem we face with refractors, what we call the mechanical problem. This is another image of the same telescope. This is the lens, this is the eyepiece. This is all empty. This is where the light gets diverged into a single point here. The mechanical problem again is because you're putting so much weight at this part of the telescope, you might break it, and it's a serious problem we have. It's hard to fix it. Another problem we have with the refractors is something we call chromatic aberration, and I'm gonna explain that to you. So this is the lens that we usually use at in the telescope. When you have a photon, a white color coming from your star, now the white color is made from the different rainbow colors, so red, green, blue, and so on. One problem we face with lenses is that the lens would refract the different colors at different angles. So as you see, when the white color comes, it gets refracted. The red color goes all the way to this point. It gets fixed here. The green color meets here. The blue color would meet there. But this will not give you a good image. This will give you an image similar to this one, what we call chromatic aberration. It seems that the colors are over each other, but they are not in phase to each other. For you to get the best result, you should refract all of these photons, all of these colors into one single point. And if you do this, you will get such a clear, sharp image. So this is the problem we have. You can relate this to a similar example you might be familiar with. When you want to take an image with your phone, sometimes you need to focus your image. And this is kind of similar to what you are seeing here. This is some kind of an out of focus image. And out of focus images can be caused when we use lenses, because those different colors will not be refracted at the same point, so you get something like this. but this won't be helpful if you want to do science. You want something sharp and good as this. So to brief this out, refractors were the first used telescopes. They were first designed probably 500 years ago, and they served us very well, but they have limitations. They have two main problems. One is the heavy lens. It's very heavy, so it causes mechanical problems. And the second problem with refractor is that they cause what we call chromatic aberration, and this is what I have just explained. Now, today we use another type of telescopes. We use reflectors telescopes. And the main difference between reflectors and refractors would be in the lens. In reflectors, we don't use lenses. In reflectors, we use mirrors instead of lenses. And instead of using one lens, we use two mirrors. This is a sketch. This is a sketch of a reflector telescope. You see it's a tube highlighted in black. In the refractor example, we placed one large lens in this region, right? And sometimes we have another lens, but forget about the other lens. So let's assume this is a refractor. We would have placed a lens right there. Now, in a reflector, we use two mirrors. We put one mirror here, a small mirror, and another mirror here. This is it, and this is it, okay? So what happens is that the light is coming from this direction and from that direction. The light will go all of its way. It will reach mirror 1. Mirror 1 will reflect the light into mirror 2. Mirror 2 will reflect the light back into the eyepiece, and this is where you would put your magnifier to look at the object. So let's follow the sketch again. You have a star right there. It is shining, giving photons. Photons will go inside the tube, inside your telescope. These are the lights moving their way inside the tube. You have a mirror here that you have designed. It will reflect the light back to the second mirror. The second mirror will reflect the light again all the way to the eyepiece. In this region, you put the magnifier. It magnifies your image and it shows you what you are looking at. These are the reflectors. And all modern telescopes are reflectors. They are cheaper. It is easier to handle mirrors than to handle lenses also. So this makes them cheaper, and they don't cause any mechanical problems because you have two mirrors in this case. You have one here and one there. While in a refractor, we mainly have one lens at the end of the tube. So there are many advantages when we use reflectors, and all of the modern telescopes are reflectors now. This is an example of one of the large telescopes we have today on Earth. You see one here, what you see here as one is the second mirror. What you see here in two is the first mirror. So the light will come from the stars. It will hit on the first mirror. The first mirror will reflect back the light into the second mirror. The second mirror will reflect back the light into this hole right there, and this is where you put your eyepiece, a magnifier which magnifies the image of the star you are looking at. So please try to relate how telescopes works. Try to sketch them in order for you to understand them better. This is a mirror being produced for a telescope as well. You see, and this is the hole. This is similar to the part you see here. So this is how we do telescopes. Yeah, here you see more telescopes, all pointing towards the stars. Here you see space telescopes. I've told you earlier in this chapter, and we have discussed this before, that the Earth atmosphere, it blocks most of the light coming from the stars, and it only allows the visible color, which means rainbow colors right there, and it allows the radio waves to pass through the atmosphere. All the gamma rays, the X-rays, the ultraviolet, the infrared, they all get blocked by the atmosphere. So on Earth, if you look here on the images of telescopes on Earth, most of them are visible telescopes, these ones. Some are radio wave telescopes because we don't have problems with detecting radio waves on Earth. But if you want to look at stars in infrared or in gamma rays or in other colors that are being blocked by the atmosphere, then you have to send the telescope all the way above the atmosphere. So you have to send them to space. These are some of the telescopes we have in space. They look at stars and in different wavelengths. And yeah, so this is the idea of why we send telescopes to the outer space, and this is something we have already talked about. So let me give you an examples of some of the telescopes. So this is Hubble Space Telescope. You see light comes from this direction. This is you have the smaller mirror here. The light goes in all the way. You have a mirror inside. It gets reflected back to the second mirror, and then the second mirror will reflect back the light, and we will able to see them here on Earth. So don't worry, this might sound like a complicated sketch, but it is very similar to what I have shown you earlier. But what you should know is the Hubble Space Telescope is one of the most important space telescopes we have ever built. Another example would be the Very Large Array, what we call VLA. And in fact, this is not one telescope. This is a combination of 27 independent telescopes in New Mexico. This is one out of the 27 telescopes we have. If you look at this telescope, assume you have a star here, it's shining, the light will go all the way to the dish here, it will be reflected back to the antenna here, and this will be connected to your computer inside this observatory, and this is where you analyze the data. So the larger the diameter of this telescope or of this dish, the more photons you will be able to collect, and the better the image will become. And don't get confused, this dish is you can think of this as a mirror, although it doesn't look like one, but you can think about it just like you think about mirrors. These are the collection of telescopes we have for VLA, the Very Large Array. And this is very powerful because all of these 27 antennas, all of these telescopes would be looking at the same time at the same object. So you're gonna have a much better image. Think of the new iPhone we have. The new iPhone has 3 different cameras. The 3 cameras will take the image of the object at the same time, and then your iPhone will actually stack these images together to give you the best resolution image. In this case, you have 27 cameras, 27 telescopes, all looking at the same object at the same time. So you're gonna have the best possible image. And just that you know, all of the telescopes that look like this one here, like a dish, like satellite dish, these are radio telescopes. Okay, these are telescopes that observe in radio waves. The ones that you are more familiar with, you see in images, the one that I have shown you earlier, are more of a visible light telescope. Yani, just for me to be clear, this is a visible light telescope, because obviously these telescopes, this one for example is different than that one. Yes, than these ones. So yeah, and we also have a better telescope. It's not called VLA, it is called the Very Long Baseline Array. So in this example, we have so many telescopes around the Earth, distributed around the Earth in different regions. And all of these telescopes again will be looking exactly at the same object, so that they can give you the best quality image. Now the main difference between these telescopes in VLBA and VLA is that at VLA here, all of the telescopes are just close to each other, looking at the same object. While in the VLBA you have different telescopes, each one placed in a different country and in a different region. So you're gonna be looking at the same object at the same time from so many different telescopes that are distributed around the Earth, and this gives you an even better image for what you are looking at. So yeah, this is the idea of the telescopes. This is another telescope. very similar to what you see as very similar to what we use here on Earth for you know, as a satellite for TV and so on. This is an image taken for Saturn using an optical telescope. This is an image taken for Saturn using a radio telescope. So you see, if you want to understand this planet, it will not be enough to take one image with the optical telescope. You really have to take another image with a radio telescope, and even another image with an infrared telescope, and so on. The more photons you have from for your object, the more you will be able to understand it. Yeah. So in this video, I only show you a zoom in for an image taken through a telescope for the central part of the Milky Way. So you see how powerful a telescope can be. Everything we see so far are stars found in the Milky Way. These are some colors here. Probably these are clouds of gases, nebulas making new stars. Now if I forward this even faster, we're gonna reach all the way to the center of the Milky Way. And you see this telescope is showing us stars. These are stars at the center of the Milky Way, in the bulge of the Milky Way. And you see these stars. Look at this one here, right there. Look what happens. So these are the stars. At some point the star is moving, and then all of a sudden, oops, let me go back here. This is easier to explain. So look here. Look at this star. You see it's moving, and then it's going really fast for some mysterious reason. It seems that this star is orbiting around a black object right there. And this is similar to how our planet orbits around the sun. When Earth is very close to the sun, it moves really fast. And then when Earth is further away from the sun, it moves slower. And in this case, this star right there is moving fast every time it's going close to this region. And I'm gonna play this again. See? It's moving fast. It's moving fast. But I don't see any star here that is causing that other star to move that fast. And this was one of the first proofs that there is a black hole right there at the center of the Milky Way, which is causing this star and other stars also to be moving in that manner that we see in this video. You see? So yeah, this star is orbiting around a black hole at the center of the Milky Way, and we cannot see the black hole, but we can see what the black hole is doing to the nearby star. It is making the nearby star orbit around it. And this is an image of a black hole taken in 2019. So this is really all I wanted to say about chapter 6. You can watch this video for James Webb Telescope. It's a 40-minute video. It is a new telescope that will be launched soon, and it will be very, very important. It will show us a lot, and it will tell us a lot about the universe and about exoplanets and about the Milky Way and about so many other different topics. So this is mainly chapter 6 in brief, and if you have questions, you can let me know.